LSP to reach the core router. This means that normal IGP routing would prevail within the PLP. You cannot use the ping or traceroute commands on routes in the Inet.3 or Inet.6.3 routing table. For BGP next hop resolution, it makes no difference whether a route is in Inet.0 or Inet.6.0 or Inet.3/Inet.6.3. The route with the best match, longest match, is chosen. Among multiple best match routes, the one with the highest preference value is chosen. That's interesting. So it's going to choose the route with the longest match, no matter if it's in the .0 table or the .3 table. Note, the install destination prefix active statement is not supported on static LSPs. When the install destination prefix active statement is configured for a static LSP, the MPLS routes do not get installed in the Inet.0 routing table. All right, so let's cross that one off. Didn't quite understand what they were talking about, but it called out the .3 tables explicitly, which are going to be important to at least have in mind during this test, because it's definitely a part of the curriculum. Now, it's a part of the curriculum for route reflection, but as I said, I was unsure. I was unable to find information about it at the time where I loaded this up, and that's the time where I would have Googled it and really tried to find information for it. But let's just kind of try that again. Maybe I didn't. .3 reflection. Yeah, so this looks really good. Inet.0.com, Junos OS route reflection considerations. Yeah, this looks pretty essential here for me to have gone over before this test. It looks like it's, let's see here. So you've decided on route reflection being your BGP scaling mechanism of choice. Everything is set up and the provider edge PE routers are exchanging VPN routing information with an out-of-path route reflector like this. In the above scenario, traffic is never forwarded through the route reflector. To be able to set up BGP sessions with all of the other PE routers, the route reflector is running OSPF with the rest of the network. Let's check the Inet.0 table on the route reflector. Okay, so they're using Junipers as well. We can see that the route reflector has a route towards the loopback address of all the PE routers. BGP sessions between the route reflector and the PE routers have already been established. The out-of-path route reflector is not involved in any label distribution, leaving the Inet.3 table completely empty. Looks like we're all set. However, when we look at what happens next, when a PE1 advertises a subnet for a C1 routing instance, we can see that there is not a lot of route reflection going on. In the output above, we can see that the PE1 router is advertising a route for a routing instance named C1. The source of the routing update is its own loopback IP address. On the route reflector, we can observe the following. We verified that the PE1 router has send the routing information towards the route reflector. Why is it then that we aren't seeing anything on the route reflector? So the route is hidden. The BGP L3 VPN.0 table contains all IPv4 VPN routes, and by default, these routes are resolved in the Inet.3 table. Since our route reflector is not involved in any label distribution protocol, it is unable to resolve the received routing updates. Routes that cannot be resolved are hidden and not reflected by our route reflector. This leaves us with a problem. What we want to accomplish is a situation wherein the route reflector actually reflects the routes. The Junos OS offers us various options to make this happen. Let's discuss and examine the following situations to our problem: enabling a label distribution protocol, configuring static routes, and changing the route resolution and using a rib group. Using a label distribution protocol, the fact that the route reflector is out of path means that the route reflector doesn't need to be burdened with a label distribution protocol. This doesn't mean that it cannot. We can fill the Inet.3 table by simply enabling RSVP signaled LSPs towards all the PEs, or by having the route reflector participate in LDP. Let's go with LDP and do a quick set protocols MPLS interface all and set protocols LDP interface all. In addition to this, we also configure the MPLS address family on the relevant interfaces. After doing so, we can verify that we learned all the necessary LDP routes like this. So this is going to be, yep, Inet.3, perfect. Since the routes towards all the PE routers are now present in the Inet.3 table, the route reflector should have no problem reflecting the CE1 route to PE6. Let's verify this by using the following command. Even though this will work fine, this option does require the route reflector to exchange additional routing information with the rest of the network. Let's look at other ways to achieve our goal without introducing an additional burden like this on the route reflector. But it sounds like if we're, okay. So this is interesting. We're trying to populate that .3 table, but it says, it doesn't say what method we use, but we can use any one of these methods. I would probably just do the LDP method for the test. It seems like one of the easier ways. Using a static route to populate the Inet.3 table, instead of turning on LDP, another quick and easy fix can be a static route. Instead of configuring a static route for the usual Inet.0 table, we can configure one specifically for the Inet.3 table like this. Set routing options rib Inet.3, routing information base, so you can actually choose the table that you modify. So you got to choose Inet.3. Static route 192.168.1.1/32, reject. After configuring this route, we can observe the following. So we've got our Inet0 tables full of OSPF routes. But now we've got a route in our Inet.3. A static route is placed inside the Inet.3 table. This enables the route reflector to resolve all the PE1 VPN routes and reflect them towards the PE6 router. Since this would only make the route reflector resolve PE1, we could install a route for a subnet containing all the PE routers, like so. In this case, a reject route was created. Discard or receive would have worked all the same. The difference is that a discard route will not elicit a response from the routing engine, and the receive option will install a route towards the routing engine. Since the route reflector does not need to use the Inet.3 route to forward traffic, the type of static route does not really matter. Altering the default route resolution. After removing the static route from the route reflector, the initial problem is back. Let's solve the problem by instructing the router to simply make use of the PE addresses it already learned. The RR is participating in a single area OSPF with the rest of the network. Wouldn't it be easy if we could just tell the route reflector something like, look at your Inet.0 table, if you can resolve it there, it's okay to reflect it? Well, with Junos OS, you can. Telling the route reflector to start using Inet.0 for VPN routes can be done in the following way. Set routing options, resolution, rib, BGP.VPN3.0, resolution, ribs, Inet.0. I think this is definitely going to be the way I want to do it. This looks like the easiest way. This statement tells the router that routing information from the Inet.L3VPN.0 table is to be resolved in the Inet.0 table. Now, even though our Inet.3 table is empty, the VPN route is reflected by the route reflector. With the current configuration, the route reflector will use all information inside the Inet.0 table. To narrow it down, we could contemplate the introduction of a policy that limits the resolution to a specific subnet like this. The end result can be verified by using the following command. Copy information using a rib group. There is yet another option that Junos OS gives us. We can make our route reflector resolve routes by using rib groups. Rib groups can be used to place routing information from a single source into a group of tables. The use of rib groups can quickly escalate the complexity of an infrastructure, but it's a pretty powerful tool nonetheless. In this specific scenario, by using rib groups, we can make the Junos OS place OSPF routes into the Inet.0 and the Inet.3 table. In order to make this happen, we have to alter the configuration in two separate places. First, we have to create the rib group under the routing options stanza. The second application of the rib group under the protocols OSPF stanza. The configuration of the rib group can be done as follows. The rib group will make sure that all routes normally placed in the Inet.0 table will be placed into both the Inet.0 as well as the Inet.3 table. For this reason, the Inet.3 table is configured first. Yeah, I'm not sure I'll be using rib groups. I'll finish reading this though. The second part of the required configuration is the application of the rib group. This is configured in the configuration stanza where the routes would normally be learned. In our case, this means that we will apply the rib group under the OSPF stanza like this. After committing this configuration, we can observe the result by consulting the Inet.3 table. Since all we really need in the Inet.3 table are the loopback addresses, IP addresses of our PE routers, this may be a bit much. Luckily, we can also apply a policy to a rib group. Let's create this policy and apply it to the rib group like this. After applying the policy, the Inet.3 table looks like this. And with the Inet.3 table looking like that, we can see that the VPN prefix is reflected once more. Nice. The Junos OS operating system has a lot of tools that can be used to manipulate routing and forwarding information. It's these tools that make Junos a very versatile OS for routing. Hopefully, this article has shed some light on how these tools can be made of use in a scenario with an out-of-path route reflector. So yeah, let's I kind of wish I had that workbook. We'll add this to the list of things that I've done, cross it off too. Yeah, and then let's so that's pretty much it. That's exactly what is going to be on there. I think having one of those methods to make sure that when you have a route reflector that your routes are going to make it into the Inet.3 table as well as the Inet.0 table. So this looks interesting. I'm going to read this too. Oh, it looks like it's an example as well. It's just showing the configuration. But this looks like it would be good to read. I'm going to include this in here. All right, so this is an overview. And it's for configuring route resolution on route reflectors. This example shows how to change the default resolution behavior on a route reflector to use Inet.0 for next hop resolution instead of Inet.3. One scenario for route resolution is when you have a label switch path configured on a route reflector to a provider edge PE router. And when the PE routers only peer with the route reflector, this can result in routes being hidden. To resolve this issue, you can change the default resolution behavior to use Inet.0 for next hop resolution. By default, the BGP.L3VPN.0 routing table stores all VPN IPv4 unicast routes. This table is present on any router that has layer 3 VPNs configured, including PE routers and route reflectors. When a layer 3 VPN router receives a route from another layer 3 VPN router, it places the route into its BGP.L3VPN.0 routing table. The route is resolved using the information in the Inet.3 routing table. This means that when BGP receives a route destined for table BGP.L3VPN.0, the protocol next hop, received BGP next hop, has its forwarding next hop recursively determined from the Inet.0 table. The resulting route is converted into IPv4 format and redistributed to all routing instance name Inet.0 routing tables if it matches the VRF import policy. On a route reflector with no attached customer edge routers, the resolution rib BGP L3VPN.0 resolution ribs Inet.0, which we read about before. Configuration causes routes in the BGP.L3VPN.0 to use, table, to use the information in the Inet.0 table instead of the Inet.3 table to resolve routes. You should not use this configuration on a router that is directly attached to a CE router. In other words, do not use resolution rib BGP.L3VPN.0 resolution ribs Inet.0 on a PE router. Well, yeah, you're going to use it on a route reflector. What the heck? If you want both Inet.0 and Inet.3 to be used, you must configure both as in set resolution rib BGP.L3VPN.0 resolution ribs Inet.0 Inet.3 in brackets. So in this example, the policy limit resolve routes limits the route resolution to only routes learned through ISIS. If you omit the import policy, all routes in Inet.0 are evaluated and potentially used to resolve the protocol next hop. If you do not want to resolve against all entries, you use a policy to filter for a subset of the routes from the tables that are used for route resolution. One common example is when you resolve against all routes in Inet.0, except the default route 0/0. Although the import statement is used in this configuration, no routes are imported or copied. Rather, the import policy name configuration limits the set of possible routes that can be considered for route resolution. the resolution rib BGP.L3VPN.0 resolution ribs Inet.3 configuration is useful when a BGP route reflector is not in the forwarding path. In other words, there are no ingress LSPs at the route reflector. Consider the case where RSVP is the label signaling protocol and RSVP is configured full mesh at the edge routers. The route reflector needs to be able to reflect the routes. To do so, BGP is expected to perform a route resolvability check if a layer 3 VPN route is received, but the next hop is not in the Inet.3 table. The route cannot be resolved because the router is not in the forwarding path. An effective workaround is to use the information in Inet.0. The metric information in Inet.0 is useful for choosing the best route, even though it cannot be used for forwarding. An alternative approach is to make sure that LSPs are configured on the route reflector. This hop happens automatically if you configure LDP. So yep, this is exactly what we read about there. Unfortunately, it's kind of yeah, so let's take this whole thing up to here and put it in there. I want to keep that because this explains, I think, exactly what this topic is about. And then let's move on. So these are kind of duplicate sources. I just thought I listed them both because I wanted to take a closer look to see if they actually are duplicate or there is some difference between them. But I'm pretty sure they're exactly duplicate. It's just for some reason that other one is a subsection of that one. But yeah, understanding BGP route reflectors, understanding BGP route reflectors is the same thing. Okay, so I would like to go through this. I think this is going to cover both. Let's see what I have loaded up here. Okay, this is interesting. This is I'm surprised I have that. Oh, I do. Okay, so sweet. We're gonna get plenty of practice with this. I'm surprised I have that one saved under here and then the other one saved under there. Maybe I got them flipped or something because it looks like this is going to be more relevant to that Inet.3. But let's just dive into the lab on route reflectors. So there's the reading, there's an example configuring a route reflector that I have set up in GNS. I might need a little bit of a break before I go through on this, but hopefully I'll come back to that and finish the reading, finish the example, and then maybe go on with some of this more advanced stuff. So route reflector belonging to 2 different clusters, route reflector, optimal route reflection, route server. Yeah, so yeah, let's do it. So I'm going to take a break, and then when I come back, we're going to be learning about BGP route reflectors. So stay tuned.